Now we'll talk about the last of the four fundamental spaces of linear algebra, the null space of A transpose. You were given A, what is the null space of A transpose? Well, one way to go about it, and actually probably the easier way, if this is all you were asked for, is to just transpose A and find the null space of A transpose the way we said find a null space. This is one way. So, okay, here is A transpose. We went from, let's see, 3 by 4 to a 4 by 3. We do row operations to get it into reduced row echelon form. Its rank is 2. Let's see, there's 3 columns, 2 pivots. So you're going to get 3 minus 2 is 1. That's what your dimension is going to be. And you use the pivot rows, or the rows with the pivots in them, to write scalar equations. This one means y1 plus y3 equals 0. This one means y2 plus y3 equals 0. Solve those and use the 1, 0 trick, but we don't need to do that here. So its dimension is 1, and here's a basis. You just said y3 equals 1, and the y1 and y2 come out of it. That's finding a null space, really. But there's another way to go about this. Here's what the null space of A transpose means, right? You want to find all the y's so that this is true. Well, we can transpose both sides here, right? When you transpose a product, you take the transpose of each one, but reverse the order, right? So I have y transpose times A equals 0, and 0 went from a column vector, now it's a row vector. Same with y. Y was a column vector, y transpose is a row vector. So now we're looking for all these y transpose to make this true. And that's why instead of calling it the null space of A transpose, we often call it the left null space. We're looking for all the y's that make this true. And actually what we want is that space, the span of all these y's, and then we want to find the dimension of that span and a basis for that span. So we're looking for the y transpose that make this true. Now assume we do some elimination on A, the original A, not A transpose. E, again, is the culmination of all the row operations, which culminates in a matrix that you multiply A by, and we'll end up with U in row echelon form. Well, the bottom rows of U, because it's in row echelon form, will be all zeros. Well, if any rows are all zeros, they're going to be at the bottom. That means, because remember, when I have a product, A times B equals C, every row of C comes from a row of the front thing. So an all zero row of U will come from the corresponding row of E, the bottom rows of E. In fact, the bottom M minus R rows of U will be all zeros, where M is how many rows of A and R is the rank of A. That means the bottom M minus R rows of E each satisfy this equation for this Y transpose. You know, the rows of E that correspond to the all zero rows of U satisfy that they're a Y transpose. And because E is an invertible matrix, that's going to mean all its rows are linearly independent. So that the bottom M minus R rows of E when we transpose them back, form a basis for the null space of A transpose. That was kind of some complicated logic. I hope you followed it. But now, well, now that all we need is, well, how do we find this E? Because all we need is the rows of E that correspond to the all zero rows of U. So here's a way to do it. The way we found an inverse using Gauss-Jordan elimination. You augment the A matrix with an identity matrix to the right. It has to have the same number of rows as A has rows. So here, these left 4 columns come from A, the right 3 come from the identity matrix. Now we start doing row operations until you get it into row echelon form. Look at the left side, the A part. It's got a row of all zeros. So the rank of A is 2. We know that. There's a pivot. There's a pivot. And look what we have here. E, remember, means all the row operations. We had, this here was A and I. Now we did E to both sides, so the whole thing, which distributes this way. EA is the U, EI is just E. We have E on the left. On the right. E is on the right here. And here's an all row of U, all zero row of U. There's only one. So this is the basis. Actually, its transpose is the basis for the left null set, or the null set of A transpose. Hope you followed that. It seems kind of complicated. I'm going to summarize all 4 spaces in the upcoming video, but now we've done them all. The row space of A, the column space of A, which is you could call the row space of A transpose. So we have the row space of A, the row space of A transpose, the null space of A, and the null space of A transpose. It's kind of a full set. And we'll get into, I'll do an example of all 4 in an upcoming video.